Good morning, everybody. Thank you, Mike, for the introduction, and sorry about the mess up. The paper I'm going to present today is about dynamically scaling middle boxes. This work was a joint work with Dan Williams and Hani Jamjoom from IBM Research and my advisor, Andrew Warfield. So what is the problem that we are tackling today? You see, we have all these scale-out applications on the cloud, Netflix, Pinterest, so on and so forth. You have your own nice app that auto-scales dynamically on the cloud. Thing is, you also want middle boxes on the cloud to sit in front of these applications, load balancers, application delivery controllers, VPN gateways, etc. Let's say you have your own nice little app on Amazon that's just scaling dynamically, and you decide to put an IDS, something like Bro, in front of your deployment. You want the middle box also to scale. The problem is, the middle boxes are not engineered for elasticity. Why? Consider the scenario like this. We have a standard scale-out setup where when your middle box is overloaded, you decide to launch another replica. Great. But then the load on M1 is still there, and M1 is still overloaded even though you're redirecting new flows to the new replica. So that's a hotspot. Or you could resolve the scenario by, let's say, scaling out generously and have tons of middle boxes around. Great, that's over provisioning, and you might end up with a scenario like this. I hate this, sorry. You might end up in the scenario like this, where when your app scales down, you will have 4 or 5 row instances, each having 1 or 2 flows. And you cannot scale in this setup. Why? Because there are flows in each middle box. And why can't you scale in this setup? Because these flows have state, and this state is stuck inside each of these middle boxes. So now that we know the context of the problem, the question is, how can we actually dynamically scale these middle boxes? Scale them in a way that's amenable in a cloud setup. The first insight, actually the only insight that we make is, the only insight that we made is that middle boxes are basically flow-oriented machines. Each flow is an isolated execution context. And a packet comes in, gets assigned to a flow, accesses all state within the flow, and it goes out. It probably accesses some other state with respect to the within the virtual machine. But it does not touch state belonging to other flows. As you can see, there's a green flow with a green box, red flow with a red box, and so on. Great. So now that we know how the middle box is structured, what if we take this middle box, replicate it, split this flow table such that we have 2 replicas handling the same flow table? We can dynamically scale this whole set, the middle box tier, by just distributing this flow table. Great, the problem is solved. Well, it's not just as easy as it sounds. In order to ensure that this setup works as intended, we need to first understand the state that's residing inside this middle box. Let's take a typical middle box like this. We have a complex application logic, flows come in, packets go out. Okay. The most important piece of state inside the middle box is the flow state, which is naturally partitioned, and it's a freebie, as we saw earlier. So that is solved. Then there's a little bit of state that's problematic, which is the shared state. If you were to have multiple replicas, we have things such as like threshold counters, statistics counters, etc. That needs to be kept coherent across replicas. Okay, so we can manage that. And then that's about it. This is all we need to care about when you want to scale a middle box. The rest of the state in the middle box is something that the developer does not have to care about because it is specific to a replica. Things like buffer caches, other processes in the OS, your background tasks, or kernel bookkeeping information, etc. It's ephemeral, and its state is valid only with respect to the processing associated with a single packet. That brings us to a contribution. How do we dynamically scale middle boxes? We present to you the SplitMerge concept. Take this middle box, for example. We have ephemeral state, coherent state, and state that is partitioned, which is basically the flow table. Let's say the middle box has one network interface. Now, when you want to scale out, we split the middle box to 3 replicas, distribute the flow table across all the 3 replicas. And then when you want to scale in, we just basically merge the 2 replicas. And what do we do when we merge? Just concatenate the flow table between the 2 replicas to one single flow table. Notice that throughout this process, the coherent state, the consistency of this coherent state is maintained. The network interfaces in each of these replicas remains unchanged. In other words, they all have the same MAC and same IP. The ephemeral state diverges. I don't care about that. So in this case, as far as the application is concerned, it thinks that it's operating on one giant middle box that just scales out and scales in dynamically. And that basically is the core idea behind the paper, and that's about it, yes. So now, let's move on to the implementation aspect of things. How do we realize a system that supports a split merge abstraction? We built a system called FreeFlow that is basically a BMM-based runtime supporting the split merge abstraction. All the application has to do, or I as a developer of a Middlebox application have to do, is modify the application code to just annotate the flow state. Once that is done, FreeFlow will take care of the rest. By rest, I mean splitting and merging mailboxes, deciding when to split, and managing the memory associated with the state, etc. I encourage you to read the paper, which contains all the gory details about memory management, etc. For the talk, I'll focus on how flows can actually be migrated between replicas, and which is basically the core founding principle behind SplitMerge. Let's take the FreeFlow. Let's see how the FreeFlow system is architected first. Consider 2 replicas with each with its own ephemeral state. There's coherent state, which is maintained consistent, and each has its own set of flows. We put this on an SDN. The first thing that we need to do is to manage the state inside the application. So we introduce a library that the developer would interact with, and the library would manage the state for the developer or the application. The FreeFlow library will take care of maintaining the consistency of coherent state, and will take care of partitioning and rebalancing flows. Then we need to ensure that the flows go to the correct replica. So what do? We actually added a module to the SDN controller that tracks the location of the flow states in every replica, and then programs a flow forwarding rule such that the flows reach the right replica. And finally, to bind all of these together into one big system, we have an orchestrator component that decides when a split or a merge operation happens. It implements various user-defined policies for elasticity. So we've seen how the FreeFlow system is architected. So I, as a developer, would want to know, how do I interface with this system, and what do I have to change in my application? This is the API that FreeFlow library provides to the developer. The top part is for managing the partition state. I allocate memory, access the flow state via the library. The bottom part is for managing the shared state. I'll talk about this API in a bit more detail in the following slides. So now that I've taken my application, modified the code to tag each piece of state as partition and coherent, what does FreeFlow do? We program the FreeFlow system automatically programs the flow forwarding rules in the network such that the flows reach the right replica. In this case, as we can see, flows B and C are in replica 2, and flow A is in replica 1. The forwarding rules, as highlighted, are going to the right replica, even though both replicas have the same MAC and IP. Now, let's see how we can migrate flow B from replica 2 to replica 1. The first thing that we need to do is to stop supplying input to the flow, or input to so that the application will stop accessing the state. So we delete all the flow rules and start buffering input packets either at the controller or at the target. And then, once the application has stopped accessing the flow state, we move the state to the other replica. Once the state is at a different replica, we re-inject the buffered packets back into the target, and reprogram the flow forwarding rules such that they go to the correct replica. Okay, so now let's see how we can manage coherent state. You might think that, okay, maintaining coherent state means having strong consistency. These counters are going to have a really bad impact on performance. Well, that is absolutely true. For example, consider this code snippet. If the middlebox wants to update a piece of counter for every packet that comes in the system, if this counter was to be maintained in a strongly consistent manner, in other words, if we have to take a distributed global lock for every update to this counter, the performance would be abysmal. But then, after looking at a whole bunch of middlebox sources, at their specifications, what we realized was most middleboxes do not require this level of strong consistency. There are no such things as global mutexes or anything of that sort. They can, in other words, but then they can actually tolerate eventual consistency. Consider this code snippet as an alternative. The middlebox does a ton of updates at high frequency locally. Then, when it wants, it can push the updates to the other replica or pull them. In other words, synchronize on demand. This periodic synchronization allows us to scale, at the same time share data across multiple replicas. Let's move on to the evaluation. The paper has a whole bunch of benchmarks, micro benchmarks, and macro benchmarks evaluating various aspects of FreeFlow. For this talk, I'll focus on 3 macro level experiments that illustrate the key features in FreeFlow. Here are the 3 experiments. The first one, I'll talk about how we can scale out without creating hotspots. Second one, how the system can actually scale in a resource efficient manner. And finally, we'll show how FreeFlow can actually make a real middlebox, something like Pro, elastic in the face of a load burst scenario. Let's revisit the hotspot situation. In the traditional style, we added a new middlebox. The new flows are going to the new middlebox, and the first one is still overloaded. With FreeFlow, what the orchestrator does is sheds the load. In other words, it migrates a whole bunch of flows from M1 to M2 such that the load is balanced across both replicas. And the net output is this. The graph shows the maximum end-to-end latency observed by a client when the flows pass through a synthetic middlebox. As you can see, when the hotspot occurs, the end-to-end latency starts peaking from 10 milliseconds all the way up to 70 or 100 milliseconds. Once the hotspot is resolved, it comes back to the pre-hotspot levels. Whereas without FreeFlow, even though you added a new replica, your performance is still the latency effects are still there. Sometimes it peaks all the way up to 100 milliseconds, which is an order of magnitude higher. This graph shows the impact on average end-to-end latency before and after the hotspot resolution. Let's look at a scale-in scenario. Consider this setup, which is something like a well-scaled out setup. There are 4 middleboxes. All of them are well utilized and equally loaded. Great. Now, consider a best case scenario, which is actually very rare. All flows in M4 die, followed by all flows in M3, followed by all flows in M2, and so on. In other words, in the traditional scale-in setup, or with FreeFlow, if you want to scale in, you just kill a middlebox. In this case, when all flows in M3 die and M3 is M4 is die and M4 is empty, just kill the middlebox and consolidate. This gives us this nice sawtooth shaped graph, where at each peak represents the point where we kill a middlebox, we consolidate setup from 4 to 3, 3 to 2, 2 to 1, and so on. Consider the worst case scenario, which probably happens a lot. There are 4 middleboxes and the same setup. If the load decreases evenly across all replicas, such that we have a setup like this, then we might end up with something like this, where there are 4 replicas, all of them are operational with a few flows each, and the system utilization goes all the way down to 0, because it's, you have to keep all replicas operational because they have flows in them. The graph shows, the green line shows that as time proceeds, the utilization gradually degrades all the way down to 0. Now let's see how FreeFlow handles the same scenario. When the load goes down, the orchestrator sees that like the utilization of the middle boxes have gone down, but then it sees, you know what, I can actually consolidate all the flows into 3 middle boxes instead of having 4 around. So we have something like this, where we have 3 middle boxes, utilization is higher, we did not kill any flows, we did not lose any state, and we are basically scaling in as the application deployment is also scaling in. We'll end up with a scenario like this, where we basically scaled in from 4 to 3, 3 to 2, 2 to 1. In other words, the final graph would actually be something close to the best case scenario. Basically, FreeFlow provides the best case utilization, whether it's a best case scenario or the worst case scaling scenario. Now let's see FreeFlow in action for a real middle box like Bro. We ported the event engine in Bro to FreeFlow, added support for a set of protocols, and added support for SQL injection detection attacks. Our experimental setup consists of a web server tier and a gateway through which like a bunch of HTTP flows pass through, each of which contains SQL injection attacks. Bro is installed on the gateway. We have a load burst scenario where before the load burst, there's one replica, which is one instance of Bro, which is more than enough to handle the load. And then when the load burst happens, that one instance is not enough, and we'll see how we can scale that. And then after the load burst, once again, that one instance is more than enough to handle the load. The first type of scaling is no scaling. In other words, we didn't do good capacity planning. So the performance of the system degrades. In other words, by performance, I mean the attack detection ratio. It degrades when the load burst happens, and then once the load burst ends, it slowly starts climbing again. So now the other alternative is to over provision, have enough replicas around such that it can handle any sort of load burst. Then we have a system, we have a graph like this where, before the load burst, there are 2 replicas, the system is underutilized, but then there's no impact on performance. When the load burst happens, there's basically, again, 2 replicas that are well utilized, there's no impact on performance, and when the load burst ends, once again, the performance goes down. But then, with FreeFlow, we have 1 replica before the load burst, great. When the load burst happens, the orchestrator sees that the replica is overloaded, it decides to split the replica, rebalance the load. There's a small blip in performance during this process, and we have 2 replicas now. Once again, well utilized, performance is back to 100% attack detection, and voila. And then, when the load burst ends, the orchestrator sees that, oh geez, the utilization has gone down. It decides to merge the 2 replicas into 1. Once again, there's a small blip in performance as the flows are migrated. When that is done, we basically have 1 replica, well utilized, performance is back to 100% detection. So in summary, this tweet summarizes the whole idea behind our work. SplitMerge enables balanced elasticity in virtual middle boxes through dynamic partitioning and consolidation of state and flows amongst replicas. That concludes my talk. Thank you for giving me an opportunity. I'd be happy to take questions.
Hi, Masood Mushrif from University of Southern California. Did you assume that the flow table entries doesn't depend on each other and you can migrate them arbitrarily anywhere?
Yes, I mean, each flow is an independent, isolated execution context.
Yes. And do you have any suggestion for selecting where the new middle boxes should be, for example, to minimize the traffic overhead, or actually trying to balance the load based on the resource?
Right, so what we've designed in this work is basically the mechanism by which you can actually split and merge, and we have left the policies up to the user in terms of like, how many replicas you want or where you want to place the replicas up to the user. So yeah, so that part is the policy dependent aspect.
Anthony Nicholson from Google. And so this might be a bit orthogonal, but your initial example seemed to talk a lot about if you want to compose commodity middle boxes, just buying intrusion detection systems off the shelf or that sort of thing. But your talk was talking about you had to actually modify the code to do all of this, obviously. So have you thought much about any sort of way to get similar or approximate wins, but using off-the-shelf middleware? It's definitely unrelated to what you talked about, but. So because most of the wins that you got obviously came from modifying the source to use the API, but just wondering if you thought about the more general problem of.
You mean like, can we do the same split merge for general class of applications?
Yeah, or you might not use the same technique, but
just without modifying
code.
About
this, yeah.
Right. So there are two schools of thought. One is like you can, without modifying code, you can continue porting systems to the cloud with legacy and like start scaling. That's when you still have the same situation like hotspots or scaling inefficiencies. Second school of thought is, what, we have a new system, let's re-architect applications in a new way such that it can actually take care of good, advantage of the elasticity. And we decided to take that approach, and when we decided to take that approach, we found that, okay, this model of scaling actually works really well for that.
Yeah, Chuck, NEC Labs, Princeton. I have a question about the coherent state across the middle boxes. Now, are you completely eliminating the need for locking across the boxes, assuming eventual consistency?
Yes, because if we were to have a lock, like in sense, if you were to have something like a global mutex, then your middle box is not even going to scale on a multi-core. So our notion of based on the middle boxes that we have looked at is things like counters do not require full strong consistency, and when that is not required, eventual consistency is more than sufficient to handle most of the scenarios. So and we did not eliminate, it still supports it, but yes, your performance would not be as good as you want.
So have you come across applications that do require consistency? Eventual consistency is not enough? No,
we haven't. From the sources that we have looked at, most of them were counters in this, and so we have not come across things that require we need exact strong consistency for the whole system as such.
Thank you.
Yan Chen from Northwestern. So a related question with the coherent state. So for example, in the Bro, intrusion detection system, there are multi-dependent flows that, one detection can involve a lot of flows. So did you try to evaluate how much this, if you have to replicate all these states, then, well, you're going to have state explosions because you have pretty much copy everything to all the replicas. Did you try this multi-flow detection problem, since you are already using the Bro as your example?
Yes. So that was one of the things that we actually encountered, which we call as a partitioning granularity. So if you're doing, let's say, maintaining a counter that's at a subnet granularity, like you're monitoring all flows from a subnet, you can either choose to keep all those flows in the same replica so that you don't have to even, worry about replicating those counters, or you can decide to spread out those flows across multiple replicas, in which case you will have to replicate those counters. It's a trade-off between the granularity of partitioning of load versus the hit that you take for these counters. And from what we saw for all the Bro policies, there were only few things that had interflow dependencies, policies that were available open source. Only a few things had these interflow dependencies, interflow counters to be precise. And yes, so those seem to there wasn't that much state that needed to be scaled across. It was few counters as such. It wasn't a state explosion as you put it as.
Okay, we can talk about that.
Steve Tarzia from VaporStream. So if you're going to re-architect the middle boxes and you want to support elastic scalability, why not make them totally stateless, push everything out to a distributed database where you can get eventual consistency there very easily with modern NoSQL distributed databases?
Well, so middle boxes are not like endpoint applications. So it's
What's the difference?
Precisely. So, you see, as an end application like a web server, I can handle 1,000 requests per second. But as a middle box, I'm going to be handling 1,000,000 packets per second. And I want to be accessing my flow state immediately. And I don't want to go to a database, even if it's like 5 millisecond or 5 microsecond latency to go and access my flow state from database. Database will end up becoming the bottleneck at some point, right? So this becomes a different class of problem. Thank you.